Okay, so we are starting with very fundamentals of probability theory, and we were on this slide last time. We defined the mean as the area, basically expected value of x. In case of continuous variable, you do by integration, and in case of discrete variable, you do it by summation. So probability of value being xi, you multiply that and you get that thing. Well, the variance is actually the distance from the mean, and so the variance is the expected value of x minus mu whole square. So either you do in the case of discrete variables by probability, or in case of continuous variable by integration. The standard deviation of variance is what? What is the standard? The square root of variance is standard deviation, and so the coefficient of variation is standard deviation upon mean. Now, generally in our work, we prefer coefficient of variation to variance, and we prefer coefficient of variation to standard deviation. Let me tell you why. Suppose x is in instructions per second, IPS. Then the mean is in what unit? IPS. Okay. We could call it MIPS, million instructions per second. So what would the variance unit would be? The square of instructions per second, right? And so if your mean is somewhere around 1 or 2 MIPS, the variance could be square of that, something in the, and if suppose your mean is 10, variance could be 100. That sounds too big, first of all. Second thing is, if you change that unit from MIPS to IPS, so now your mean is in something like 10⁶ something, and variance is 10⁻12 something. So it's totally unimaginable. It's not really easy to grasp. So standard deviation is better than variance because at least it is in the same unit. So you can say, well, the mean is 10 and the standard deviation is 5. Same unit, right? Comparable. But coefficient of variation is better because coefficient of variation has no units. It is dimensionless. So whether you measure it in IPS or whether you measure it in MIPS, coefficient of variation is 0.2, period, done. Okay? So it does not depend upon the unit. And it will be the same regardless of what you measure the mean in. And therefore, it is very easy for us to guess that 0.2, whether it is low or high, it is normalized by definition. Right? Now, I'm not going to say whether 0.2 is low or high. Why not? Can anybody guess why 0.2 could be low or could be high? What does it depend upon that 0.2 is too high a variation? Well, it's not a mathematical answer. In some cases, a small variance can cause a lot of money. Think about flying, security, anything that, throwing a bomb or something, and if you're off by a centimeter, you kill children, and so, you see what I mean? So the idea is that the variance, how much variance is acceptable depends upon what effect does it have on the system, what system does with that error. Right? So mathematical books will tell you 0.2 is small or 0.1 is small or less than 1 is small and all that. That is only for mathematicians. In the real world, you have real dollars which depend upon that number. So in some cases, 0.2 would be considered small. In many cases, it would be considered very large. If you're off by 20% when throwing a bomb, you would be fired right away, right? So that's the situation, okay? All right. Let's move on to the next thing. Oh, actually, this is just an example of the previous thing. So we had the example of the distribution, and that was uniform distribution. Remember the uniform distribution from 1 to 3. So minimum is 1, maximum is 3, and the probability is half, anywhere in that range. So if you want to calculate mean value, then you take the expected value from minus infinity to plus infinity, x times fx dx. Now minus infinity to plus 1 up to 1, it is 0 anyway, so you don't need to worry about that. And from 3 to plus infinity it is 0, so you don't need to worry about that. So you really need to take the area under the curve between 1 and 3. And the area under the curve x times fx. Fx is half in that region, times dx. Now you will have to know integration, differentiation and all of those things. So if you do integrate x upon 2, the integration is x square upon 4. And then you put number 3 there, you get 9 by 4 minus, then you put a 1 there, you get 1 by 4, and the mean is 2, which is what you could have gotten without too much mathematics. I mean, if your thing is uniformly distributed between 1 and 3, the mean is 2, right? But this is a very simple distribution, and in other cases you really have to use the formula. All right, so we found the mean. The variance is xi minus mu whole square fx dx. So xi, actually from minus infinity to plus infinity, I shouldn't put xi here. It should be simply x. This is not a discrete variable. So basically you put x minus mu is 2. So x minus 2 whole square times fx is half dx from 1 to 3. Now x minus 2 whole squared, if you integrate that, it becomes a cube by 3. So that becomes x minus 2 raised to 3 divided by 6. And now you put x is equal to 3, you get 1/6, minus, you put minus 1, and that becomes minus 1 upon 6 plus 1 upon 6 gives you 1/3. So the variance is 1/3. Everybody feels comfortable doing this integration differentiation? Okay. Alright, since this is 1/3, the standard deviation is square root of that, 1 upon square root of 3. The coefficient of variation is sigma upon mu, which is 1 upon square root of 3 divided by 2, so 1 upon 2 times the square root of 3. So next one is covariance. Covariance has to do with two variables. So far we are talking one variable. Now we have two variables, x and y. Both of them are random, but they are somehow related. And therefore the covariance is the expected value of x minus mu x times y minus mu y, expected value of the whole thing. It is denoted by sigma xy. And if you multiply these two, you would get basically expected value of xy minus expected value of ex ey. So that is basically, this is mu x and this is mu y. So this is expected value of xy minus mu x mu y. You can do that basically very easily, because what happens is if you multiply this, you will get 4 terms, xy minus mu xy minus mu yx and minus mu x mu y, right? 4 terms. And you take the expected value of each of those, and basically everything will cancel, the 2 terms will cancel out and these 2 will be left over. Basically this term will appear 3 times, minus plus something like that, so you will end up with minus. Anyway, for independent variables, if the variables x and y are independent, then the covariance will be 0. The expected value of x times y will be exactly equal to expected value of x times expected value of y. There is no relationship. Okay, so this will be equal, that means this will be 0 for independent variables. Now this conclusion is only one way. If the variables are independent, then the covariance is 0. If the covariance is 0, does not mean that the variables are independent. The variables could be dependent, but the covariance could still be 0. So this is just one way. Although independence always implies 0 covariance, the reverse is not true. So simply because exy equal to ex times ey does not mean they are independent. And this is the problem, that there is no test in the world for independence. You cannot prove statistically some things are independent. Only thing you can do is keep proving that they are not dependent by this method, not dependent by this method, not dependent by that method. So there are several tests for dependence. And you can pass all those tests. More tests you pass, more you feel that you are getting too close to independence. But that's the only limit. And basically, you cannot conclusively prove that things are independent. All right. So all the tests are designed for dependence, not for independence. Okay. So there is one test for dependence, is this one, which says that if the dependence depends upon covariance, and so correlation coefficient. Now, so now this has a unit. If x is measured in something and the y is measured in something else, this has a unit of product of those two units. If x and y were both MIPS, then this will be MIPS squared. Just like variance. So we need something which does not have a dimension, and that is called correlation. And the correlation is simply this, which is actually denoted by sigma. Sorry, this is denoted by sigma square x by. So the top letter, this would be sigma square x by. So the top letter is sigma square x by. So you get then that whole thing divided by sigma x sigma y, which is the variance of x and variance of standard deviation of x and standard deviation of y, not the variance square root. So this is dimensionless. And not only dimensionless, this is also bounded. Bounded between -1 and +1, as opposed to the variation coefficient of variation, which is not bounded. Coefficient of variation could be anywhere from 0 to infinity. Okay, this one is always between -1 and +1, and obviously 0 means not dependent. -1 means perfectly dependent in the opposite direction. So if one goes up, the other goes down, and +1 means perfectly dependent in the same direction. So if one goes up, the other goes up. Dependent only. We are not talking about independence. I'm sorry. If I say independent, perfectly dependent. And now this correlation is always misused in many fields. Like they will say, well, and I have to think of this live right now, an example, and you can probably think of an example in news media. They come up with that, they found out that this thing depends upon something else, right? Or I'm just going to make it up. Your chance of getting cold depends upon your hair color. All right. So how does it happen? Because they took 50 people, took their hair color, and took how often they get sick or get cold, and there is a correlation. Correlation does not imply dependence. Dependence implies correlation. If two things are dependent, they will be correlated. But if they're not dependent, still there could be correlation through third variable. And through third variable means that that x depends upon z and y depends upon z, but x and y do not depend upon each other. So it's not a transitive relationship. Is that people who have certain color, they use certain chemicals, okay, and those chemicals could be causing the problem. I hear one day they say, oh, coffee causes cancer, and the next they say, no, coffee improves the chances of not having cancer. Similarly for heart attack, everything, that was supposed to happen last year, it doesn't happen this year. That's a different sample. It's a different conclusion. So be careful when you really, it just gives you some indication that there is a dependence, and then you have to really go to the system and find out. Mathematics cannot tell you the answer. Correlation. Now we go into more than two variables. So if we have k variables, x1, x2 through xk, and we take some weights, a1, a2, ak, then the expected value of the sum is equal to the sum of the expected values. Expected value of a1, x1 plus a2, x2 plus ak, xk is equal to a1 times expected value of x1 plus a2 times expected value of x2, and so on and so forth. This is always true. regardless of dependence. But if you take the variance, then the variance will also add up only if they are independent variables. If there is a dependence, then it doesn't add up. Only for independent variable, variance of a1 x1 plus a2 s2 plus axk would be like that. Alright, then we move on to the next concept called quantiles. And the quantile is like percentile. You all have heard of percentile. The real statistical term is quantile. So the quantile is actually measured between 0 and 1. So when we say 0.9 quantile, we mean 90 percentile. When we say 0.95 quantile, we mean 95 percentile. Okay? So the quantile is measured between 0 and 1. Percentile is measured between 0 and 100. And so when we say that the alpha quantile, we mean 100 times alpha percentile. So alpha is generally 0.9 or 0.95. So we talk about 90 percentile or 95 percentile. Okay? So that is basically the value at which the cumulative distribution becomes alpha. So this is our cumulative distribution. And if we draw a line at 0.75 and we read the value of x, at that value, 75% of the values are less than that value. Right? So that is the 0.75 quantile of x. If we take 50% and we draw a line at 0.5, so that is the 0.5 quantile or 50 percentile. Similarly, you have 0.25 quantile or 25 percentile. Now looking at this graph, which is the density function, it's kind of not easy to say this thing, but basically all it is saying is that the area under the curve on this side is equal to the alpha. So when you take 75 quantile, 75 percentile and draw a line, then the area under the curve is 75%, which is 0.75. Alright, so there are some special names for these quantiles. For example, the 50 percentile is called the median. And then this is called quartile. Q-U-A-R-T-I-L-E, quartile. So this is the third quartile, second quartile, first quartile. Quarter, 1/4. Alright, so you have first quartile, second quartile. So you are in the first quartile, means you are in the bottom 25%. You are in the top quartile, means you are in the top 25%, right? So this is, these are quartiles, and the median is the medium on the 50 percentile. And mode. Mode is the value at which the density function is maximum. It has nothing to do with this one. Basically, this is the point at which the slope of the distribution function is maximum. The slope is maximum, so you cannot really see the slope that easily. But on this graph, you can see, because this is simply the slope, right? So the maximum point is called the mode. So the mode of x is this value. Alright, so everybody understands now quantile, percentile, quartile, median, mode. Then we move on to normal distribution. Now, the normal distribution is this function. Density function is 1 upon sigma square root of 2 pi e raised to minus x minus mu whole square upon 2 sigma square, and it goes from minus infinity to plus infinity. And it's very, like you never really use this expression for anything because it's very difficult to handle this expression to begin with. But this is the most common distribution. That's why it is called normal distribution. So you take any random number from any distribution, but take a lot of them. Take a lot of them, then the sum will be in most cases. Now here's the thing, there are few exceptions which we'll talk about towards the end of this class. But for most cases, for almost all cases that we generally deal with, the sum is normally distributed. This is also called the bell-shaped curve. So the thing is, the name normal simply means that this is what normally happens, is that you take any distribution and you take a lot of numbers, add them up and take the mean, and therefore the mean is normally distributed. So the mean from any distribution is normally distributed. Okay, let me qualify basically this one, because some people will start. So in what cases would the mean will not be normally distributed? So there are exceptions when the variance is infinity. Okay, and we will not really encounter those most of the class. At the end of the class, we'll talk about that in the end of this whole semester. What are the variables that have infinite distributions? In infinite variance. Okay, generally we don't encounter them here. So for everything, basically the mean is normally distributed. A normal variate, so we do use the notation, and that is the most important thing, is that instead of writing all this, we call it n mu sigma, where mu is the mean, sigma is the standard deviation. And if it is 0 and 1, which means the mean is 0 and the standard deviation is 1, we call it a standard normal distribution, and we use our unit normal distribution. And we are going to use it very much throughout this book, throughout this chapter, throughout this course. Unit normal distribution. A unit normal distribution is one which has a mean of 0 and the standard deviation of 1. So if you go to another example of normal distribution is, if you go to a toll booth, the cars are coming 15 lanes, and there are 15 of those toll booths. Generally, there are more cars in the middle and less cars in the extremes. That's the normal distribution. Or if you throw some things, mostly the things will fall mostly in the middle, few will go on the sides. That becomes a normal distribution. So bell-shaped curve happens many places. All right, quantiles. So normal distribution also has a quantile. And we are going to use those, we call them Z, the letter Z. So the alpha quantile of normal 0, 1 is called Z alpha. If it is not normal, then it also has the quantile, and that quantile is equal to mu plus Z alpha times sigma. So if it is 0 and 1, then it is exactly equal to Z alpha, otherwise it is mu plus Z alpha sigma. So what that means is that if you want to get the quantile of a standard normal distribution, you can just read it from the book. At the back of the book, which some of you have, at the back of the book there are tables A1, A2 and A3 about the normal distribution. Okay, page 628 onwards. So A1 has the area under the curve, A2 has the quantiles of the unit normal distribution, and A3 is the commonly used values. Let me go to the commonly used values. So 99%, which is 0.01 quantile, is not 99. Actually, let's talk about 95 level, which is 0.05, is 1.96. All right, and we remember this because we need that number so often that after certain use you will also remember this. Right now you may not, but 1.96 is the 95 or 0.95th quantile of normal 0, 1. Okay, but if you don't have normal 0, 1, you have some other mean and some other standard deviation, then all you have to do is take the mean plus 1.96 times whatever the standard deviation is, mean plus 1.96 times the standard deviation, you will get, for that variable, the probability is 95%. There are two reasons for the probability of the normal distribution. First is the sum of n independent normal variables. First of all, the normal distribution is good in itself. You take one of them, it is normally distributed. You take two of them, the sum is normally distributed. You take three of them, the sum is normally distributed. So you can take any number of normally distributed variable with different mean and standard deviation, of course. The sum is normally distributed. So very easy to handle. When things add up like that, it's very easy to handle. Mathematicians like it. But it's not just by itself, it's also that you take any distribution and the sum has a normal distribution. Alright? And this is called central limit theorem. Central limit theorem says that when you have a lot of numbers from any distribution, the sum is normally distributed. And that's why the experimental errors are normally distributed. Because you have taken care of all the factors, but there's lots of other parameters that you have not taken care of, and they are causing the variation in your measurement, and therefore the errors are normally distributed. They are at least assumed to be normally distributed. And in our class, we'll learn how to verify that assumption, that something is normally distributed. Okay? But the reason they are assumed to be normally distributed is because they are caused by many, many factors. Each factor gives a little variation, and the sum of all these variations becomes normal. Yes, so then we will change the model. That's the whole purpose of this course actually, is that we emphasize that you have to verify all your assumptions. And one of the things we teach you later on in the course is how to verify these assumptions in a manner so that even your manager can understand everything visually. So we use statistics, but only to the extent that it makes sense. Yeah, if it is not normally distributed, then the model is not good. Alright, so first you have to understand why we assume normal is because it is the sum of many, many things that we don't know, right? Okay. So here's first homework. The execution time of queries on a database is normally distributed with a mean of 5 seconds and a standard deviation of 1. So the mean is 5, standard deviation is 1. So now you have to find out what is the probability of execution time being more than 8 seconds. So you need that table. In that table you have to figure out where 8 will happen, what quantile it will happen, and that is what we are asking. What is the probability of execution time being less than 6 seconds, which is a similar question, but we are asking on the less side, less than 6 seconds. So you have to just measure from minus infinity to 6. In the previous case, you are measuring from 8 to infinity. More, this is less. What percent of responses will take between 4 and 7 seconds? So now we are asking what is the probability of being 4 and 7. So, we are not taking minus infinity or plus infinity. We are just taking from 4 to 7. Again, that table will help. What is the 95 percentile execution time? So again, you have to find the 95 percentile, and given, if you remember the number 1.96, you can do that right now in your head from 1.96. The reason you need that table is because you can't remember the rest of the table.